Good afternoon again. So, how was assignment 1? Let's start with that. Did you made it on time?
Yeah, sort of.
Good. So, looking forward to the presentations tomorrow. Yeah, today's session will be shorter. So, before the break, I will finish the lighting and colors that I didn't manage to finish last time, and in the second half we will discuss exam date and like assignment 2 when Christopher joins, and then you can take a break before tomorrow's presentation and after I'm sure a stressful weekend. So yeah, just quickly go through what we were talking about last time. So the 3 key factors that contribute to color: the illumination, the spectral reflectance or material properties, we can say, of the object, and the observer or sensor. And then we went through different illuminants like fluorescence, incandescence, different spectral power distributions of them, and human perception with 3 color sensitive cones, conditionally blue, green and red, or like short wavelengths, medium wavelengths and long wavelengths ones, and also rods for anyone remembers what rods are used for in our eyes? Yeah.
Luminance vision, like brightness.
Yeah, in low luminance. Yeah, when the lighting, in a dim illumination. Yeah, that's true, and it's color blind. So that's the reason why we don't see colors at night when we see just the outlines. And then we talked about color deficiencies and why it's important to consider in gaming and in the design. A few words about color constancy, color models, and then with this super important equation that we need to understand how it works. So does anyone remember, and can anyone explain what the rendering equation is and what do we have and what's happening here? Yeah, feel free to.
Yeah, so the output of the equation is the light strength and the light color of a specific point, and it starts with if it's a lamp, then it will maybe have emission or not. So the first part there, the E, is the emission part, and that's only applicable for light sources, basically.
Yeah.
And afterwards, you calculate the surface reflectance with the BRDF.
Yeah, that's correct. Yeah, absolutely.
Yeah, which takes into account the surface color and the mostly, right?
Yeah, surface properties.
And how glossy it is and all that. And that's multiplied by the light color.
And this
and
is.
the angle is it's a factor of the strength based on the angle and how much of the surface is lit, and the light will be weaker if it's a bigger surface.
Yeah, exactly, absolutely. Yeah, that's perfect explanation. Yeah, we have the resulting color that is combination of emission and reflection, that what is reflected from the light, and we have this attenuation factor. Yeah, thank you for great explanation. Yeah, we have this attenuation that you have already mentioned, BRDF, and except for reflection that we have for opaque objects, there are some other stuff happening for translucent objects, transmission and refraction that we have here, where the rays are refracted and bent. That's why we have this displacement of the straw, and subsurface scattering. That is illustrated very well here, while BRDF only deals with the surface. Subsurface scattering also takes into consideration all the interaction with the photons and between the photons and material that happens within the object after the penetration of the light. And then what was a major problem for gaming?
Performance mostly?
Yeah, exactly. So the perfect case that is given by rendering equation would take like immense amount of time that is not really feasible in rendering, where we're interested in real time. And then we discussed different rendering techniques very briefly, like ray tracing, photon mapping. There was a question, and I have another slide on that. Caustics, and yeah, path tracing, scanline rendering, that is actually decreasing the amount of information we want to render based on what we see in the scene, and different light sources that I will go to. And finally we came to the fog model, so where we have several components like ambient color, diffuse color, and specular color. Or maybe this slide is more relevant. So can anyone explain the fog model? Like what are the components, what is ambient light, what's diffuse and specular light? Yeah.
Okay, so ambient light is sort of the base color that just exists in the environment. So maybe at night that's a dark blue, and day it's sort of still a dark blue but a different hue maybe. Diffuse is the direct lighting coming directly from a light source. So if you have a light here, the diffuse would be like from that light only, and then the specular is emulating the reflections of light sources, and it's also based on the camera angle from the light to the viewer, but the diffuse is constant from all directions.
Yeah, so it's in many different directions. Yeah.
Specular, you don't see the highlights unless you're at the correct angle.
Yeah,
like to the light.
Yeah, that's correct. What is the key difference between ambient light and diffuse and specular light? What's like most important factor? Yeah, direction.
Ambient doesn't have it. It comes from all directions.
Yeah,
so
directionality. Yeah, that's right. And yeah, that was more or less it for the last lecture, and today we're just gonna continue with that. First of all, I will start. There was a question, like we said, ray tracing doesn't really deal well with caustics and like complicated path, while path tracing and photo mapping are better for that. But there was a question, what's major difference between them? So the first thing that is usually mentioned in the literature is that path tracing is unbiased, so the only error you get is just like statistical variance, and after having many samples you more or less converge to the true values, so you don't introduce any artificial bias, while photon mapping is a biased rendering that takes some shortcuts to end with the pleasing or satisfactory result, but might not always be accurate. For example, some smoothing of the noise and stuff like that. And unbiased ones are usually used as a reference to compare the performance of other rendering techniques. And yeah, photo mapping is usually said to converge faster to the satisfactory result, while we need many samples for path tracing. And here, I don't know whether you see it well, we have very noisy one when we have one sample per pixel, and then we double the samples. And as you see, when we increase the number of samples, the noise goes away gradually. And also, like, there are still like path tracing isn't perfect with complicated light path, with indirect illumination. So there are like other versions, improved versions of that, like for example bidirectional path tracing. And later in a few lectures we will have a separate session on Mitsuba renderer, where you will be able to play with all these different techniques. And I think it's a better way, like, rather than just bringing some theory from the literature, it will be easier for you to play, like have some hands-on lab and see how different techniques work and how they impact the results. So we will address this issue later. Yeah, to continue, this is like old way of addressing lighting in OpenGL, so I won't go deep into details, but if you see like the syntax like this, it's just deprecated now, so just skip that, and just you need to know that this is the old OpenGL and the tutorial is the old one. So what it works, what it looks like in modern OpenGL is like a very simple principle. So we have the basic color of the particular pixel, so the material property we can say. And for ambient lighting, we simply find the dot product of the two vectors. So if we have the ambient light, something like this, and we have the color of the pixel that is blue, we get then finally the color that is equal to this vector. And in fragment shader, it's implemented like exactly as it's given here. So we multiply ambient coefficient, or like constant ambient light, with surface color RGB and with the intensity. For diffuse lighting, it's a little bit more complicated. So here you see that this is a very good example from car paint. We have top coat layer that is usually very shiny, glossy, because it's flat, and we have lots of specular reflections here, while the substrate layer, where the paint layer is rough, so the surface has different directionalities, and we have more or less diffuse reflection, where the light is reflected into many different directions, and the combination of those two gives like the car paint we see like in daily lives, that they are glossy, shiny, but they also have this kind of diffuse component. And the way it is implemented in OpenGL is actually very intuitive. We start with finding the illumination direction, and this is just to take it in relation with the position of the pixel. So we just subtract that, and we get the vector that shows the lighting direction. So this is the illuminant position, this is the position of the pixel that is illuminated, and we get this direction. And then we normalize to get the vector that shows the direction from the pixel towards the light source. And afterwards, who remembers what normals are used for? There are like several uses of them. Why do we need surface normals? And what are normals first? Yeah?
Normals are the direction of the space, or like the point where like the outwards direction, sort of.
It's
they're like the normal of the table would be straight up.
Yeah, perpendicular 90 degree.
Yeah. And they're used for for example, the attenuation of light, or for lighting.
Would you like to add? You were.
Oh, I was just going to say that it's not necessarily for each surface, it's also per fragment, because some surfaces may use normal maps to adjust the normal.
Yeah, you can find the mean. Yeah,
yeah,
we'll get to that with flat shading. Yeah, and another use of it is to identify whether the area is visible to the observer at all. So in this case, we find the dot product between the normal and the illumination direction. And the reason we compare compare it with 0 and take maximum is to avoid the negative values, because in that case it will be equal to 0, because the normal, this means the normal is facing away and the color will be simply black. And finally we get a diffuse color that is just a product of material color, the illumination color, intensity, and diffuse factor that defines this angle and the spread we have considering the angle. I mean, like the one that you addressed here. And also manually we can control how, like when it's 90 degree we have all the light intensity concentrated, while the angle decreases, this amount of light is spread towards the surface, so we have this attenuation and diffuse like spread. That is back to, but you can also like manually control the diffuse factor to, like artists do that, to play with appearance. Just let me confirm that it's streaming properly. Yeah, okay. For specular lighting, actually, what was important to detect, to see the specularities? We had a slide on that. So in which case do we see that here? Like if the specular reflection is directed towards the camera or the observer, we see that. But if the camera doesn't coincide with the specular component, we don't see this point as a gloss, like, or specular reflection. So it's important to consider the angle between observer or the camera and reflection. So what we have here is that incidence vector, so the incident light ray vector is simply just the opposite to from surface to light. So we had the vectors that showed from the illuminated point towards the light source, and the incident angle is just like that vector turned around by like if we have the point and this vector shows the direction towards the light source, the incidence vector will be just like this one turned around from light source towards the point. And we have reflection vector that is found by reflect function and takes as parameters incident vector and the surface normal. And this reflect function is already implemented for you in GLSL, so you can directly call it. And then we need to find the vector from surface to the observer or to the camera. That is just normalization of camera position and the surface position, like in the previous case. And what is important here, the cosine angle again between angle between the between two vectors. The one is reflection vector and one is the direction towards the observer. So what we actually calculate here to get back is the angle between the vector that goes, that is one is a reflection vector and another vector that goes to the observer. So we want to find this angle, the cosine of this angle, to find how close the observer is towards the reflected direction of the specularity. So we got, so if the difference is, so if the observer is located at the reflection like direction, the angle is 0 and the cosine is equal to 1. If we have 90 degrees, so if it it's perpendicular and doesn't really observe that, then cosine is equal to 0, and that's how we use that parameter here. Yeah. And then we have a specular coefficient that is this cosine angle in power of some material shininess parameter. So this parameter depends on the material properties, so how shiny or glossy the surface is. So you can, like, artists can play with this parameter to have more shiny, more glossy surfaces or less shiny ones. So it's kind of a variable that you can use to control the material and surface appearance. And finally, surface the specular component is found as the specular color. The coefficient that we found here, considering the shininess and the cosine angle, like cosine of the angle between reflection and the observer, and the intensities. So the larger the shininess is, the parameter is, more shiny the surface appears, and also nearer the angle between the reflected ray and the observer, more bright and shiny this area appears. Because if we have the 0-degree angle, it's like perfect specularity. And one code optimization proposal. So can anyone explain this? If we check for diffuse factor, like how can we take the shortcut in this case to just avoid unnecessary calculations? We just talked about that a few minutes earlier, yeah?
It's not, then you're not looking, then you're at the back of the face, right? So you
Yeah, exactly. So, yeah, it's this thing. So we have to make sure that the dot product between the normal and the illumination direction is positive. So if it's, we can directly check if this negative, this means that this this point is not visible at all, so we don't really care about care neither about a diffuse factor nor about specular factor. So if this product is negative, then we can skip this one because we won't have specular component. That's kind of shortcut we can take. And if it's greater than 0, then it makes sense to start calculating specular component. Well, this is more or less it with specular and diffuse lighting. And there were like 2 other factors that were not included in the Phong model, but are important to consider for realistic representation. One is attenuation. So the idea is that farther the light source is, less strong, so weaker the illumination is. If I take, for example, my flashlight and illuminate this pencil from here, and then if I start moving this light away and away, so it will start becoming weaker and weaker. So it will impact the color less and less farther I take the light source. So the distance, except for the directionality and the angles, what we need to consider is also the distance, physical distance between the light source and the point we're considering in this case. And in reality, actually, it's just like 1 over distance squared. So this is how much the intensity decreases. However, in OpenGL, we use what portion of the illumination is preserved, like in this way. So if distance is, yeah, one question, like why do we need to use this kind of representation instead of this one? Like, what is one significant advantage of that in terms of coding?
The distance is 0?
Yeah, exactly. Yeah, exactly. Very good point. So if distance is 0, we will get division by 0 error. So to avoid that, we, instead of presenting that way, we present what portion of the overall energy is preserved. So if distance is 0, we preserve 1. So and if it's infinity, we get 0 of the light preserved. And another way of controlling it is introducing some arbitrary parameter, light attenuation parameter, that if you don't really want to attenuate your light source by this law, and if you want to keep it even if you move farther, or if you want to make it weaker even if it's closer, just for some like visual effects or depending on your application. So you can introduce this light attenuation parameter and control attenuation that way. So it's actually the same thing, but multiplying d squared by some k arbitrary coefficient. So it can be either like inspired from the reality, what is preserved, or it can be something controlled arbitrarily depending on artists or programmers' needs. And yeah, finally, when we need to find a linear color, and we will see soon what linear color is and what non-linear means in this sense, is that we, before adding directional factors like diffuse and specular components, we multiply it by attenuation. And ambient is not touched by this because we don't have one particular light source that we have to measure distance to. Yeah, let's move to the gamma correction. Gamma correction is actually another thing that we need to consider if we want to have visualization that corresponds to human biology and human vision. Like if we have this kind of smooth input and if we have linear steps for representing that, we will get something like this. As you see here, like large area is not really distinguishable, while here we have several steps that are also like look very alike. So if we really want to have the steps that make sense, that's what gamma correction is used for, and then we have more, as you see, like I don't know whether you see, but you should be able to see on your displays, like more logical representation of this. So gamma correction enables more efficient usage of the bits. The trick here is that human vision is more sensitive towards low luminance areas. Like in this area, our vision is more sensitive, and we can like sense more shades here, while we are not that sensitive for the bright ones. So it doesn't make sense to have equal steps here and here. It's like more. It would make sense to use the bits to have more dense sampling here to represent all the differences we can perceive, and have larger steps here because not to encode anything that we can't perceive anyways. And if you have a look, like let's have a look at those slides. For example, for camera, it's just simply linear, like amount of photons is linearly correlated to the detected light, so sent signal. So we have like 50% of the light and 50% of the signal for the camera. But this is how the camera sees, like 50% bright, of like 50% less bright than this. So this should be, this is how camera sees it, but actually for human vision it's like completely different. So we mentioned that human is sensitive to low luminous areas, and as you see here, like even actual luminance is low. So we already start detecting light pretty well. So the difference here is also like very obvious between this one and what if we had just like equal steps. So what we need to do here is to introduce gamma correction to compensate for that. Like the idea is that if we have like this amount of luminance, we don't see like for 0.5 we don't see 0.5, we see this much, and for 0.21 we don't see like 0.21, but we are more sensitive in this area because it's low luminance area, so we like can perceive this much. So what we need to do is to introduce a parameter that will compensate that. And in this case, if we want to convert from linear values to gamma corrected or gamma encoded values, we use like this is kind of standard value 2.2 that comes from CRT displays. So we use 1/22 because the values are between 0 and 1. So by this power we get this increase from 0.28 actual luminance to the perceived one. And likewise, if we want to decode gamma from like back to the linear one, we use this one, 2.2 directly, the power. Yeah, this 2.2 comes from CRT displays where if you imagine like RGB where R equal to 1 and is compared against R equal to how much was that? R equal to 0.5, it's not twice as bright, but it's 4.5 times bright. So instead of having twice as bright when you increase from 0.5 to 1, we have 4.5 times decrease, and that's where we get this by dividing 4.5 by 2, we get this approximately 2.2 as a kind of standard value for gamma correction. But what you and yeah, here is the OpenGL implementation where you have like 1/2.2 vec3, and then you just like take each R, G, and B parameters into power of the corresponding gamma. So 1/2.2, so that if you have like this value, you take in power of 1/2.2 and you get this one, because the human sensitivity curve is this one, not, and this is the computer like or camera sensitivity, this one, and this is how humans perceive that. But there is one important thing that you have to bear in mind, that if you're using textures, if you're loading textures, it's very likely that it's already gamma corrected, because most of it's very popular to use RGB, sRGB color space, and sRGB already includes gamma correction. So sRGB is device independent color space. So if you have RGB values and if you display it on different hardware, you are not guaranteed that you will get the same perceptual colors. So they are device dependent. So different voltages for different displays give different colors. While sRGB is a kind of try by Microsoft, HP, and some like corporations to have a standard that encodes color in a way that it's device independent, and it should be in some particular fixed conditions that is taken, I think, D65 illumination that is whitish and close to what is used in modern offices and in working areas. So like the idea is that when you display an image on my screen and on your screen, the same sRGB values should give the same perceptual color. It's not perfect, but it's considered a device-independent color space that compensates for all those various factors. That's more or less it on gamma correction. And one more thing that might be interesting for you is luminosity functions. So here is the sensitivity of human eye towards luminosity, so the luminous intensity. This means that higher the sensitivity is, more brighter we see the signal, while lower, when we have low sensitivity, for this is the wavelengths across the spectrum. So if it's like a low sensitivity, we need a really high signal to see it bright. And the difference between green and red curves is that green curve is for road vision, scotopic vision is called like this night vision, the very low luminance vision, while photopic vision is regular luminance color everyday vision. So as you see, like we are very sensitive, most sensitive around 550 nanometers, that is greenish area kind of. And in order to get luminance, usually the simplest way is to take R plus B plus G and divide them by 3, but that's not very correct. If you want that to really correspond to human vision, here is the formula where like G value has highest weight, and the bluish component, and our sensitivity is very low towards blue. Blue is smallest one, and we have some contribution to R as well. So if we want to take the luminance parameter, the best approximation is green channel. So most of the information. So if you like have played with in MATLAB, if you take RGB image and separate channels R, G, and B, like the G, the green channel is the closest one to the grayscale that you want to have. So this is about luminance and our sensitivity towards light intensity and brightness perceptions. So again, yeah, high sensitivity means that we are sensitive towards amounts of light, and we perceive that bright very easily. While when we are not really sensitive, we need high amount of light to perceive like increasing brightness. And the last point for this lecture is funk shading versus flat shading. So any ideas what is the difference between those two renderings? Yeah?
The funk one is interpolated between the values, and the other one is flat per face, it looks like.
Actually, it looks like that, but it's actually the left one where we have interpolation happening. So maybe you can, any guess? Okay, I'll give you a clue. Where are they implemented in the rendering pipeline? Imagine like where can they be implemented? Yes, which one?
Flat or the other one?
Yeah. So yeah, any other input? Okay, yeah, the trick here is that for the flat shading, we have calculations made only for the vertices. It's implemented in the vertex shader, and all the rest is interpolated and for the primitive. So that's why we get this kind of flat surface, we see the primitives clearly because we have all those shading calculations made for the vertices in the vertex shader. While for the funk shading, instead of calculating the colors for the vertices only, we calculate color for every pixel. So we don't need to interpolate because, yeah?
But the normals are interpolated, right?
Normals are interpolated for flat shading. It's taken from adjacent primitives, and the average is taken. It's like 2 slides after this. Because we have color calculated for every pixel, we have this kind of smooth representation, and we don't need to interpolate between the pixels. Here is more on funk shading, and flat shading or Gura shading. We calculate lighting like for the funk, for the vertices, and then we calculate normals as an average of like all the adjacent surfaces. So the normal is the average of like this normal, this one, and the one over there. And finally it looks flat, and it looks a bit weird, but why do we need flat shading? Well, why does it make sense to be considered and discussed here at all?
Performance again?
Yeah, it's super fast. It's way faster than the funk shading, because we don't need to run the calculations for every pixel. So it can be, in some cases, it can be a good compromise depending on our needs and the application. But it also depends what kind of quality you want to get from that. This is the extra resources you might want to look into if you want to get like more details and the math and stuff behind those stuff. That's all like for lighting and colors, and then next lecture we'll have object loaders. But like, any questions so far on this? Is everything clear, or somewhat clear, or nothing clear?
I'll have to toy with it in the practice.
Yeah, that's true. So we had the lab last time, so did you manage to get like to play with the light source and the material properties and change code in the shader?
I looked at it, but I didn't manage to change much meaningful.
But you will, the best way, actually, I agree with that. Best way of learning is actually practicing, and you will need that for the assignment too. So don't worry, you will face this in assignment too. Okay, then, as we don't have full second hour, and we just have a few like practical stuff to mention, we might take 5 minutes break and continue then. Is it okay?
Yeah, as long as I can run to the canteen and get some food.
Okay, just 5-7 minutes and we can continue.